Meet Ava. She's a video editor working on a 4K project. She hits export, and immediately, fan noise, lag spikes.
Her computer is choking. The real bottleneck? Memory.
Ava has 3 apps running: her video editor, a browser, and a render engine. All 3 are fighting for the same limited working memory. The CPU is fast, but it's starving for data.
Think of it like a chef who can cook incredibly fast. But the ingredients keep arriving late from the warehouse.
The bottleneck isn't the chef's skill, it's the delivery system. Understanding the memory path is the key to fixing lag. Your computer has 2 kinds of memory, and they are nothing alike. RAM, random access memory, is the fast working area. Storage, your hard drive or SSD, is the long-term archive. RAM is like a workbench right next to you, instant access. Storage is like a massive filing cabinet in another room. You can fit tons in the cabinet, but walking there takes time.
One cannot replace the other. You need both working together. So what happens when data moves between them? Let's look closer.
Imagine you're a warehouse worker with a huge storage room. Your desk is small, maybe room for 5 folders at a time. The storage room behind you holds thousands of folders. When you need a folder, you walk to the back, grab it, and return. That walk takes time. Every single trip costs you seconds.
If all 5 folders on your desk are the right ones, perfect. You work at maximum speed, no walking, no waiting. But when you need a 6th folder, something has to go.
A bigger desk means fewer trips. More RAM means less swapping.
Let's trace what happens when you double-click an application.
The program lives on your storage drive as a file. The operating system reads that file and copies key parts into RAM. Not the whole thing, just the pieces needed right now. Now the CPU can start executing. It reads from RAM directly. Fetch an instruction, decode it, execute it, store the result. This cycle happens billions of times every single second. The speed of this cycle depends on how fast RAM can respond. If RAM is slow, the CPU sits idle, waiting for data. Those idle moments are called stalls, and they add up quickly. Fast RAM keeps the entire pipeline flowing smoothly. Let's put real numbers on this. Latency is what matters most. Latency means the delay between asking for data and getting it. RAM latency, about 10 nanoseconds. That's the gold standard. An NVMe SSD, around 100 microseconds. That's 10,000 times slower than RAM. A traditional hard disk drive, about 10 milliseconds. That's 1 million times slower than RAM. Huge difference. There's one critical difference between RAM and storage.
RAM is volatile, storage is persistent. What does that mean?
Volatile means RAM needs constant electrical power to hold data. The moment you cut the power, everything in RAM vanishes instantly. That's why your unsaved document disappears in a power outage. Storage works differently. It writes data onto physical media. Magnetic platters in hard drives, flash cells in SSDs. Your files, photos, and operating system survive every reboot. This is why every startup begins by loading state from disk.
Now let's watch Ava work under normal conditions.
She's got her video editor open, a browser with 10 tabs, and Spotify. Each application claims a chunk of RAM for its working data. The video editor takes about 4 gigabytes. The browser tabs collectively use around 2 gigabytes. Total usage, about 7 gigs out of her 16. RAM usage is at 44%, plenty of headroom. The operating system loves having extra free RAM. It uses that free space for disk caching, a clever trick. Recently accessed files stay cached in unused RAM. So when Ava reopens a file, it loads instantly from cache.
The system feels snappy, responsive, almost psychic. No stutters, no lag, no spinning wheel of frustration.
The CPU gets all the data it needs, exactly when it needs it. This is what a balanced system looks like. Disk activity is minimal. The SSD is mostly idle.
Everything is running at peak efficiency. But what happens when Ava pushes her system harder? Let's see.
Ava opens a 40 gigabyte video project alongside everything else. RAM usage shoots up, 12 gigs, 13, 14. She's approaching the limit of her 16 gigabyte system. At 90%, the operating system starts getting nervous. It begins a process called paging, moving cold data to disk. Cold data means memory pages that haven't been used recently. The OS writes those pages to a swap file on the SSD.
This frees up RAM for the new data Ava needs right now. But here's the problem. What if she switches back?
She clicks on the browser. Those tabs were paged out. The OS has to read them back from disk into RAM. That read operation takes microseconds, not nanoseconds.
The CPU stalls. Ava sees a brief freeze.
She switches back to the editor. Same thing happens again. This is called thrashing, constant swapping in and out. The system spends more time managing memory than doing real work. This is why lag appears suddenly, not gradually.
Everything is fine until RAM hits capacity. Then it crashes hard. The solution? More RAM, plain and simple. No paging, no thrashing, no lag.
Let's look deeper at what happens during heavy swapping. The disk activity indicator goes from calm to frantic. Throughput spikes as the OS desperately shuffles pages around. But raw throughput isn't the real issue. Latency is. Each individual page fault requires a random disk access. And random access is where even fast SSDs struggle. The disk has to jump around, reading small chunks from everywhere. Every single page in operation costs real measurable time.
Stack up hundreds of page faults per second, and you get those micro freezes that drive users crazy. The mouse stutters, video playback drops frames.
All because the working set exceeded available RAM. The fix isn't a faster disk, it's more memory. Now that said, your storage drive still matters enormously. When swapping does happen, and it will sometimes, speed helps. Compare a traditional hard drive with a modern NVMe SSD. A hard drive reads at about 100 megabytes per second. An NVMe SSD reads at 3,000 megabytes per second. That's 10 to 100 times faster for random reads. So when page faults happen, the SSD resolves them much faster. Those half-second freezes become 50 millisecond blips. This is why upgrading from HDD to SSD feels transformative. Boot times drop from minutes to seconds. Apps launch instantly. But remember, SSD is not a substitute for RAM capacity. It's a safety net for when RAM runs short.
The ideal setup? Enough RAM for your workload, plus a fast NVMe.
RAM handles the working set. SSD handles everything else. Together, they create a smooth, responsive experience. Here's what we've learned about the memory hierarchy. Storage saves your data permanently. It's the filing cabinet. RAM provides fast working space. It's the desk you work on. The CPU computes at incredible speed, but needs data from RAM. When RAM runs out, the OS pages data to disk. That causes lag. An SSD softens the blow, but can't replace RAM capacity. For video editing and multitasking, 16 gigs is the minimum. 32 gigs gives you real breathing room. Ava upgraded to 32 gigabytes. Her timeline stays smooth.
No more fan noise, no more lag spikes, just smooth editing. Understanding your memory is the first step to mastering your machine. Thanks for watching. Stay curious